I'm waiting for video to start on this one. There we are. Hello, everybody. We've had a request to do a boiling point question, and trying to adjust this a little bit. We have to put molecules in order of increasing boiling point, and the things you need to consider are intramolecular forces. Sorry, start over. Intermolecular forces. Since I brought it up with the mistake, what is an intramolecular force? It's a force that holds a molecule together. They're called bonds. We are not talking about bonds when we're talking about intermolecular forces. Intermolecular forces, there's three kinds that you are responsible for. The strongest of the three is hydrogen bonding. You only have hydrogen bonding if you have a molecule with hydrogen bonded to oxygen or nitrogen. Notice I did not include fluorine. I would have if I was giving you a lecture for Chem 141. Hydrogen fluoride is not organic, so we will not be talking about hydrogen bonding to fluorine in this course. So our strongest hydrogen bonds are molecules possessing H bonded to O, and the attraction these molecules have for other molecules that have O or N in them. Okay, so what functional groups have O bonded to H in organic chemistry? Answer: alcohols, all of them, primary, secondary, and tertiary, all have hydrogen bonding intermolecular force capabilities. What nitrogen-containing compounds can hydrogen bond? You might say all amines and all amides, and you would be wrong. You need amines and amides that have a bond from N to H. That only includes primary and secondary amines, and primary and secondary amides with a D. A tertiary amine or a tertiary amide is no more polar than a normal hydrocarbon or an alkane because they don't hydrogen bond. So keep that in mind. Hydrogen bonding, strongest intermolecular force. What two functional groups have OH? Well, we did alcohols. We forgot, or I forgot to mention carboxylic acids. Carboxylic acids, if you have to choose between one of those and an alcohol that has a similar mass, go with the carboxylic acid. Not only can it hydrogen bond using its H bonded to O and the O that's bonded to H, but it can hydrogen bond with the carbonyl oxygen as well, which is not present in an alcohol. So top dog in this course for intermolecular forces, carboxylic acids. Second billing, alcohols, primary, secondary, tertiary. Why are the amines and amides of lower intermolecular forces? It's because NH is not as polar as OH. That is strictly based on electronegativity. So that ends the hydrogen bonding discussion. Next up, the dipole-dipole discussion. Those molecules have slightly weaker intermolecular forces than hydrogen bonders, and they are molecules that have mostly carbonyls for us. Now, don't talk to me about carbonyls with OH attached. That's a carboxylic acid. We already have top dog for those. Carbonyls like aldehydes, ketones, esters, and amides, even tertiary amides, have dipole-dipole attraction because carbonyl is a polar covalent bond. Oh, did I not tell you? What causes a dipole-dipole intermolecular force is a polar covalent bond? Except for the polar covalent bonds where H is bonded to O or N. I call that an extreme dipole-dipole. That's called a hydrogen bond by most people, and I have to go with that because most people need to be talked to. Okay, so What about the third type of intermolecular force? The one possessed by every molecule. London forces. Very weak intermolecular forces caused by temporary dipoles. Temporary dipoles in nonpolar bonds, because in those kinds of bonds, electrons are always moving back and forth. So if an electron is over here at any given time, that atom that is real close to those electrons starts feeling a little negative. And the atom where the electrons moved away from, the atom here, or I guess here, that atom feels positive. When the electrons shuffle back over here, this atom feels negative. And the other atom, I'm bad with directions here. The other atom feels positive. And they keep doing this. The bonds above and below each other in different molecules, so that there's always a negative above a positive and a positive above this negative. That's a temporary attraction called a London force. They're weak. But as molecules get larger, those forces add up. That's why a molecule such as a wax molecule with like 40 carbons in a chain have substantial intermolecular forces, even though they're weak. They're weak, but they're multiplied by, well, you got 40 carbons, that's a lot of bonds. So there's our discussion about the three main intermolecular forces. So what you look at first when you're comparing molecules is the major intermolecular forces present. Hydrogen bonders you want to put at the top of the list, dipole, dipoles next, and then London only at the bottom. Now, when does branching have an effect? When the intermolecular forces are of the same type between two molecules, yet one of them, and the mass is exactly the same or within like 4 grams per mole. That's when you look at branching. So in that case, when the molecules have almost exactly the same mass and the exact same intermolecular forces, the ones that are straight chains really can get close to other molecules that are straight chains. They get on top of each other tight, and they have stronger intermolecular forces. Okay? Now, here's a molecule that's a straight chain, my hand. Here's one that's branched, my hand. It's a ball. You can't get as many balls close to each other as you can these flat molecules. See how they're stacking up real tight? So the ones that aren't branched have stronger intermolecular forces. I think we're ready for a question. I'm going to share the screen. We're going to go to Spring 19, Test 1. And I sure hope I brought the video back with the students on it and not another one, because I don't know if I see any names. Does somebody want to just say hi to prove that somebody's here? Oh boy. Okay, I'm going to call this the introduction video. And I'm going to go back and make sure I open the right link and apologize to all the students who I left hanging. I'll be right back.